Hey everyone, today we're diving into something pretty cool. A study called Aligning Synthetic Medical Images with Clinical Knowledge Using Human Feedback. Now imagine this, we're not just making any images, we're crafting ones that doctors might look at and say, hey, that's what I'm talking about. This study is all about making sure these synthetic images aren't just fancy, but they actually make sense in the medical world. So let's get started and see what this is all about. All right, folks, let's jump into the why behind all this, the introduction and motivation for this study. So first off, we're facing a real head-scratcher in medical AI, making synthetic medical images that doctors can actually use. You see, it's one thing to create pictures that look real, but it's a whole other ballgame to make them clinically useful. Most current tech, well, it kind of misses the mark on capturing those super important clinical details. And here's the kicker. If we really want to make a difference in healthcare, we've got to get these synthetic images to line up with real-world medical know-how. That's what we're diving into today. Next up, we're talking about what's already out there and, well, why it's not quite cutting it. We've got these smart algorithms, right? Generative models like GANs and diffusion models, super cool stuff that's great at making images look real. But when it comes to medical images, it's not just about looking real, it's about being right, clinically right. Now, these models, they've got a bit of a blind spot. They're not too savvy with the whole medical knowledge thing. So they might make an image that looks perfect, but to a trained doc's eye, it's like, nope, that's not how cells behave. This makes it super tricky to say, yep, this synthetic image is good to go for medical stuff. The paper we're diving into today talks about this exact problem. It's like, we've got the tech to create these super detailed images, but without that clinical insight, we're kind of just making pretty pictures, not helpful medical tools. And that's what we're here to fix. Let's get into how this team is tackling the challenge and making synthetic images that aren't just impressive, but clinically insightful too. Alrighty, let's chat about these fancy things called generative adversarial networks, or GANs, in the world of medical imaging. Picture this, two neural networks, kind of like an artist and a critic. The generator is the artist, cooking up images out of thin air, and the discriminator, that's the critic, always judging, comparing those fake images to real ones. Now, these GANs are pretty clever, churning out images that can fool you into thinking they're real. But here's the catch. While they're great at the art of illusion, they're not so hot when it comes to clinical accuracy. It's like they know how to paint a masterpiece, but don't quite get the science behind the picture. And in medicine, those details, they're everything. You miss the mark on the clinical side, and well, that's a problem. So while GANs are making waves with their realistic images, they're still learning how to catch up on the medical smarts. Stick around to see how we tackle this and make GANs not just great artists, but also savvy clinicians. Moving on, let's dive into something called diffusion models. Now, these are the new kids on the block in the world of image generation. Imagine starting with just a canvas of pure digital noise, and then bit by bit, like magic, it transforms into a detailed image. That's what diffusion models do. They refine and refine until voila, you've got a picture. But here's the thing. As cool as they are, they're kind of like that friend who's great at improv but not so good with instructions. They churn out images, sure, but trying to get them to nail specific clinical details, that's a tough one. They're all about the big picture, not so much the nitty-gritty medical specifics we care about. And in medical imaging, you guessed it, those specifics are non-negotiable. We need images that aren't just structurally sound, but clinically on point too. So, the big question with diffusion models is, how do we steer this creative process to ensure the images are not just beautiful, but also medically meaningful? Stick around as we unravel this puzzle. Okay, folks, time for the main event, the proposed approach. Imagine a superhero team-up, but it's between AI and pathologists. That's right, we're bringing real-life medical experts into the loop with a pathologist-in-the-loop framework. It's like having a wise mentor guiding our AI to make not just good, but great medical images. Here's how it rolls out. Step 1. We kick things off by gathering feedback from pathologists. They take a look at the images our model generates and give their 2 cents, like, this is spot on, or nah, this doesn't look right. Step 2. Next, we take all that golden feedback and feed it into a new model. This one's job is to understand what makes an image clinically plausible. It's learning directly from the pros. Step 3. Armed with this new wisdom, we go back and fine-tune our original generative model. It's like giving it a clinical crash course, making sure the next batch of images it creates are not just good-looking, but medically accurate. So there you have it, a clever mix of human smarts and AI power, all aimed at making synthetic medical images that doctors can trust. Let's dive deeper into each of these steps and see this approach in action. All right, let's zoom in on this superhero team-up, the pathologist in the loop framework. Picture this. We've got a loop, a cycle, where AI and medical expertise dance together. It's all about teamwork, making sure every synthetic image is a step closer to perfection. First up, imagine a pathologist sitting down, eyeing these AI-generated images. They're not just looking, they're evaluating, thinking, does this image make the cut? Is it clinically plausible? This is step 1, where real medical insight meets AI creativity. Then, we move to step 2. All that valuable feedback, it doesn't go to waste. We use it to train a special model, a reward model. This model's sole mission is to understand what makes an image a thumbs up or a thumbs down from a clinical perspective. It's like distilling the wisdom of the pathologists into something the AI can understand. Finally, step 3 is where the magic happens. We take our original image-generating AI and give it a crash course with the reward model. It's like saying, hey, learn from your mistakes, buddy. We fine-tune it so the next round of images it generates are not just visually stunning, but also clinically accurate. So there you have it, an overview of this amazing framework where pathologists and AI work hand in hand. It's not just about making images, it's about making them right. Let's keep going to see how this all plays out in the real world. All right, let's roll up our sleeves and get a bit technical, shall we? We're talking about the nuts and bolts of how this whole pathologist in the loop thing works. First off, at the heart of our image-making wizardry is something called a conditional diffusion model. Think of it as a super smart artist that starts with a bit of noise and then step by step refines it into a detailed image. But it's got a twist. It's conditional, meaning it takes a bit of guidance on what kind of image we want. Now, enter the human pathologists. Their job isn't over after giving feedback once. Oh no, they're an integral part of refining these models. Every bit of their feedback is like gold, helping to steer the AI away from fantasy and closer to medical reality. And then there's the reward model, the unsung hero guiding the fine-tuning process. It takes all the insights from the pathologists and translates them into a language the AI understands. It's the compass keeping the generative model on the right track. Finally, we come full circle, with pathologists evaluating the model's output for clinical plausibility. It's like a quality check, ensuring that every image the model produces isn't just a pretty picture, but a useful one for the medical field. So there you have it, a whirlwind tour of the technical gears turning behind the scenes. It's all about combining the best of AI and human expertise to make something genuinely useful for the medical world. Let's keep the momentum going and see what this all leads to. Okay, team, let's decode some of the secret sauce ingredients in this recipe. We've got a bunch of variables that are the real MVPs behind the scenes. Okay, folks, step 1 of our journey is all about gathering wisdom from the pros. Yes, it's feedback collection time. Here's how it rolls out. First, we whip up a batch of synthetic images. Think of it as our AI chef cooking up some digital delicacies. We're talking about a whole set of images XJ and their declared cell type CJ. This isn't just random. It's all carefully crafted by our trained conditional diffusion model. Now it's showtime for the pathologists. They step in, inspect each image XJ, and give it the good old thumbs up or down, which we note down as YJ. It's like a rapid-fire round of hot or not, but for medical images. The end game of this step? A shiny new dataset that pairs each synthetic image with its cell type and the pathologist's seal of approval or disapproval. It's the groundwork for making our AI smarter and our images more clinically savvy. So there you have it. Step 1, gathering the gold. Pathologist feedback. Alrighty, on to step 2, clinical plausibility reward modeling. Sounds fancy, right? Here's the breakdown. Think of it like training a pet. We want our AI to understand what's a good trick and what's not. So we take our synthetic dataset and spice it up with some real images and mix up the labels a bit. This cocktail becomes our classifier dataset DC. Now, it's time for the reward model R-Row to hit the gym. We train it on this mixed bag of data to predict pathologist feedback. It's like teaching it the secret handshake of the medical world. Here's where the brainy stuff kicks in, the loss function. Without getting too deep into the math soup, it's essentially a way of telling our model, hey buddy, here's how well you're doing. We want it to get really good at guessing what the pathologist would say about each image. So, step 2 is all about turning feedback into foresight. We're molding our model to anticipate what makes an image a medical marvel or a medical mishap. Stick around to see how this training pays off. And now we've made it to step 3, clinically informed fine-tuning. This is where we take all that learning and really put it to work. Imagine our diffusion model as a student who's been cramming all night. Now, it's time to take the test, and we're going to make sure it's been paying attention. We're going to fine-tune this model, making it smarter and more focused on what really matters, clinical plausibility. So how do we whip it into shape? We use a special type of loss function. Think of it like a point system, where the model gets points for creating images that fit what the reward model says is good. It's all about encouraging the AI to produce images that not only look good, but make sense in the medical world. This step is crucial because it's about more than just making corrections. It's about steering the whole ship in a new direction. We're not just tweaking the model, we're infusing it with a deep understanding of what it means to be clinically useful. By the end of this step, our model isn't just generating images, it's generating trust. It's ensuring that what it creates will be a valuable tool for medical professionals. So there you have it, step 3, where all our hard work starts to really show its value. All right, let's get into the real meat of the matter with impact of pathologist feedback on synthetic images. This is where we see the fruits of our labor, folks. Picture this. We've got a before and after scene. Our synthetic images, pre and post pathologist feedback. It's like looking at one of those home makeover shows, but for medical images. Now, I wish you could see these results right here. Imagine side-by-side comparisons showing just how much our images have upped their game. We're talking both the nitty-gritty numbers and the actual look of these images. It's one thing to say our model's doing better, but it's another to see it with your own eyes. The feedback from our pathologist team isn't just a pat on the back, it's transformative. It's turned our AI from a keen student into a valedictorian in medical imagery. The quality jump isn't just impressive, it's crucial. We're seeing images that not only look more realistic, but are also more trustworthy from a clinical standpoint. So there you have it. The impact of pathologist feedback isn't just significant, it's game-changing. It's the difference between an educated guess and an informed decision. Stick around as we dive deeper into these changes and what they mean for the future of medical imaging. All right, as we hit the home stretch of our journey, let's wrap up with the results and insights from this incredible study. This is where we really see the payoff of all that hard work. First up, the clinical plausibility of our generated images has gone through the roof. Thanks to the pathologist's golden feedback and our AI's hard work, we're now looking at images that make even the most skeptical doctors nod in approval. But wait, there's more. Our model isn't just wowing in the plausibility department. It's also scoring big on fidelity and diversity. That means the images aren't just believable, they're varied and high quality too. It's like hitting a home run in the world of synthetic medical imaging. And perhaps the most exciting part? This isn't a one-off win. Our approach paves the way for continuous learning and adaptation. As medical knowledge evolves, so can our models, staying up to date with the latest in clinical concepts. So as we close off today's dive into AI and medical imaging, let's take a moment to appreciate the journey. We've seen how blending AI smarts with pathologist insights can lead to synthetic images that aren't just impressive, but truly impactful. Thanks for sticking around and exploring this cutting-edge world with me. Keep those curious minds buzzing, and here's to many more breakthroughs and insights in the fascinating field of medical imaging. Catch you next time.